Welcome to this video in which we will discuss the main DFT properties. We will see that most of these properties look similar to the properties of other Fourier transforms, however there are some important differences. The main difference is that the DFT is a periodic or circular operation. This implies that the indices of both time and frequency representations can be denoted by modulo counting. Furthermore, we will use a sub-index p to denote this periodic behavior. It's straightforward to show that the DFT is a linear operation. Shifting in time or frequency domain results in a multiplication with a complex exponent in the other domain, although we should realize that the shift is a circular shift. The convolution in time or frequency domain is equivalent to a multiplication in the other domain, in which the convolution is a circular convolution. We will show that complex conjugation results in mirroring in a circular way in the frequency domain. As a result, this implies that for real signals only half of the DFT samples are unique and have to be calculated. Finally, we will show that the DFT operation preserves energy. Because of the fact that the DFT is a periodic or circular operation, we will first discuss into more detail how to interpret indices in both time and frequency domain representations. In general, signal xn can have an infinite amount of samples. When using an endpoint DFT, we typically select the n samples ranging from time index n is 0 until n-1. The frequency indices k of the DFT result also ranges from k is 0 until n-1. The range of indices of both time and frequency representations of the inverse DFT operation are the same. The DFT operations are periodic or circular, which will be denoted by using a sub-index p in the definitions. This periodic behavior can be shown as follows for the samples xpn of the inverse DFT. By adding lambda times n to the index n, in which lambda is a positive or negative integer, we must adjust the index of the exponent accordingly. By splitting this index, we obtain a complex exponent with an index which is a multiplicity of 2 pi, which is equal to 1. And the result is equal to the sequence xpn again. This implies that we can construct signal xpn from the original signal xn by first selecting the n samples that are used in the DFT operation and then periodically repeat these samples. Typically, we use the n samples ranging from index n is 0 until n-1, which is the so-called fundamental period, abbreviated by Fp. In a similar way, it can be shown that the DFT samples xpk are periodic. From this periodic behavior of both time and frequency representations, it follows that for the periodic extended notation, that is the notation with the sub-index p, for both DFT and inverse DFT operations hold for any index. However, we only need one period, which typically is chosen in the index range from 0 until n-1. In time domain, this is the fundamental period, and in frequency domain, this is the fundamental interval, abbreviated by Fi. This fundamental interval represents relative frequencies theta in the range 0 until 2 pi. As one of the first consequences of this periodic behavior, we need to pay special attention to the shift operation. When shifting, for example, a signal xn over one sample to the right, the result is as shown on the slide. More specifically, the red sample at index n is 0 moves to index n is 1, and the blue sample at index n is 3 moves to index n is 4. When using the periodic extended signal xpn with period n is 4 samples, and then shift over one sample, It follows that within the fundamental period the n samples of xpn-1 and xn-1 are not the same. More specifically, for xpn-1 the blue sample at index n is 3 is moved out the fundamental period at the right hand side, while it enters again the fundamental period at the left hand side at index n is 0. This circular behavior can be represented by using modulo counting for the indices of the periodic extended signal. In the following slides we need an explicit expression for this modulo representation within the fundamental period. This goes as follows. Assume a shift of the periodic extended signal xpn over n0 samples, in which n0 is assumed to be a positive integer. As a first step, we can represent the shifted sample at index -n0 within the fundamental period by adding an integer amount lambda times n. Now we have to map n consecutive samples of the shifted periodic extended signal xpn-n0 into the fundamental period. The samples in the red area map into the red area at the right hand side of the fundamental period, as denoted in the figure. In this range, the samples are indexed by n minus n0 plus lambda n. If we map the following samples, indicated by the blue area, in the same way, they will be mapped outside the fundamental period at the right hand side. So these samples have to be mapped at the left hand side of the fundamental period, in which they can be indexed by extracting an extra n samples in comparison to the indices in the red area. We will use this way of indexing in the proof of the following circular shift property, which states that the circular shift in time domain results in a multiplication with a complex exponent in frequency domain. When applying the DFT to the shifted samples xpn minus n0, we can use the indexing of the previous slide. From this, we can split the summation into the following two parts. The red part, which contains the samples which are at the right hand side of the fundamental period, and the blue part, which contains samples that are shifted outside the fundamental period at the right hand side and entering the fundamental period again at the left hand side. Now we can substitute a new index m and replace the index n with this new index in the complex exponent of both summations. The complex exponent with index n0 can be taken outside brackets. Furthermore, we can split in both summations the complex exponent, which is indicated in yellow. As before, the indices of these yellow exponents are multiplicities of 2 pi, and thus these exponents are equal to 1. The resulting two summations are the same, but each of the indices run over a different part of the fundamental period. When concatenating these two summations, the results between brackets writes as the DFT results of xpk, which ends the proof. In a similar way, it can be shown that a circular shift in frequency domain results in a multiplication with a complex exponent in time domain. The circular convolution is indicated by a star with a circle around it, as denoted by the red symbol, and it is defined as the given product over one fundamental period of xp or hp. It's important to realize that the fundamental periods of both x and h have to be the same, and in case this is not true, we have to apply zero padding to make these fundamental periods the same. In the following animation, we will show all intermediate steps of this circular convolution procedure. In this example, signal X has length 4 and impulse response H contains 3 samples. Since both must have the same length, the first step is to apply zero padding. In this case, this implies adding one extra zero to the impulse response H. Then both X and H are periodically extended with period n is 4. And the periodic extended impulse response is flipped around index n is 0. Note the specific result of this flipped result within the fundamental period. The sample at index n is 0 is copied, while the other samples have been reversed in order. Then multiply element-wise the samples of xp and the flipped impulse response hp, and sum the result over one period, which leads to a resulting output sample. Then shift the flipped impulse response and repeat the previous steps. Until the end of one fundamental period. The resulting output signal Y contains the circular convolution result. As denoted in gray, it's obvious that signal Y can also be represented in the periodic extended way. Now we will show that the convolution in time domain is equivalent to a multiplication in frequency domain. For the proof of this property, we first apply the DFT operation to the circular convolution, and then switch the order of the two summations. In between brackets, we recognize the DFT of the impulse response, which has been shifted in time domain. As shown in one of the previous slides, this time domain shift results in a multiplication with a complex exponent in frequency domain. Moving the complex exponent forward finalizes the proof. In a similar way, it can be shown that a circular convolution in frequency domain is equivalent to a multiplication in time domain. For practical reasons, it's important to understand the difference between a usual or linear convolution and a circular convolution. For example, let's assume we are interested in the evaluation of the linear convolution result between signals xn of length n1 with impulse response hn of length n2. In this example, we have n1 as n2 is 4. The linear convolution result is a finite length signal y of length n is equal to n1 plus n2 minus 1 is 7 samples. When evaluating a circular convolution of the periodic extended signal and impulse responses with fundamental period n is 4, the result is shown in the slide. It's clear that within the fundamental period this result is not the same as the linear convolution result. However, when first applying zero padding up to a length of n is 7 in this case, and then applying a circular convolution, the result within the fundamental period is exactly the same as the linear convolution result. In general, we can state that the fundamental period of the circular convolution result is the same as a linear convolution result when we apply zero padding before the periodic extension up to a length which is at least n is equal to n1 plus n2 minus 1, in which n1 and n2 represent the finite length of signals x and impulse response h respectively. Together with the fact that the circular convolution is equivalent to a multiplication in frequency domain, we will present a procedure to calculate a linear convolution by a circular one, which is implemented in the frequency domain. The derivation of this procedure goes as follows. The linear convolution result of a finite length n signal x with a finite length L impulse response h results in a signal y with length m is n plus l minus 1 samples. When applying zero padding up to a length of at least m samples and then periodic extent both signal x and impulse response h, the result of the samples in the fundamental period of the circular convolution ypn is the same as a linear convolution yn. Finally, the circular convolution operation, as denoted in red in the figure, can be implemented by an element-wise multiplication of the DFT results of xpn and hpn respectively, and applying the inverse DFT to these results. In a follow-up video, we will show that the DFT can be implemented very efficiently by a so-called fast Fourier transform, abbreviated by FFT. When applying FFTs, it follows that the above described procedure is an extremely efficient way to implement a filter or convolution operation. This complexity reduction is one of the main reasons of existence of the DFT and FFT. Because of the periodic behavior of the DFT operation, the DFT of a complex conjugated signal leads to a special result. In the first step of the proof of the complex conjugation property, we apply the DFT operation to the complex conjugated samples. Then we take the complex operation outside the brackets and multiply with 1, which can be expressed by the given complex exponent denoted in yellow. Finally, we can combine the two exponents, which finalizes the proof. As a result of this property, we can derive the following for the case that signal x is a real signal. First, the DFT of x star and x is the same, or in other words, the DFT of a real signal has the given symmetry property. From this, it follows that we only need to calculate half of the DFT components. The other half can be obtained from the resulting symmetry property. More specifically, the range of DFT coefficients that we need to calculate for a real signal is given by this first equation for n odd and this second equation for n even. Moreover, when n is even, the middle coefficient is equal to its complex conjugated value. In other words, it's a real number. Parceval has shown that the Fourier transform preserves energy. Here we will show that this property also holds for the DFT. The proof goes as follows. First, we write out, according to the DFT definition, the term xp star. Then bring the complex conjugation operation inside the brackets. Then we can change the order of the summations and combine the factor 1 over n before the second summation. The second summation represents the inverse DFT operation, resulting in xpn, which finalizes the proof. Note that it seems as if there is a difference of a factor 1 over n between the energy in time and frequency domain. However, this is simply the result of the way that the DFT and inverse DFT operations have been defined. This ends this video in which we discussed the main DFT properties. Thank you for your attention.